All right.
Right? Until the primary current becomes steady, right? Yeah. When the primary current becomes steady, okay, and the induced current will end, right? Understand? No?
Okay, yeah.
Okay, so after I have interpreted the detailed process, okay, so you can to show me how to describe the switch on when the process is switched on. Okay, how to describe the counted process.
When it's switched on,
At the beginning,
the current reaches a steady value, and then in the process of reaching there, it produces a rapid changing magnetic flux in the transformer.
yes.
That produces a temporary EMF in the secondary coil.
Yeah, no problem. Okay, and what is the time? What is time? The process will end.
When it becomes steady, when the DC current reaches its steady current, the EMF will be gone.
Yeah, no problem. Okay, no problem. Okay, and look at this. The question 2, the B. When the DC current in the primary is remains on. Okay, remains on. Okay, remains on. Okay, when it remains on, what will happen? The change. The change will take place inside of the secondary coil of transformer. When the DC current in the primary coil is remains on. Remains on. Okay. How to interpret the remains on?
There's no change in magnetic flux, so there's no EMF.
Yeah, no problem. Because when the DC current in the primary coil remains on, once the DC current remains constant, the magnetic flux produced by the primary coil is constant, right? The not change, right? Okay. Because there's no change, since the electromagnetic induction requires a changing magnetic flux. Okay. So there's no voltage or no current induced in the secondary coil, right? Understand that?
Yeah.
No current, no voltage. Okay. How about the last one? Switch on, switch on. If the DC current in the primary coil is switch on, okay, how to describe the process?
I think an opposite magnetic flux will be created. Opposite magnetic flux is created, and so a temporary opposite EMF is produced on the secondary coil.
Okay, no problem. Okay, so you refer to the DC current is switch off. The current in the primary coil decreases rapidly from the steady value to the other, right?
Yeah.
Okay, when we switch off, okay, from the current will change from the steady value to the other. Okay, this causes the magnetic flux in the coil to decrease rapidly. Again, by Faraday's law, this changing flux decreases. This changing flux induces a temporary voltage, right? And the current in the second coil. But in the keyword is the opposite direction, right? It's the opposite direction you have mentioned. Understand that?
Yeah.
To the voltage induced when the current is switched on. Okay, no problem. And look at it. Look at the example tip. Okay. When we explain the link, every time we explain the link in the EM, both sides of the coil in the transformer are very common exam question. Okay, the first we have to mention the induced EM, okay, or the induced current, right? Induced current, okay, or we can use some terminology like the Faraday's law, right? Understand that? Okay, no problem.
Yeah, no problem.
Okay, so we can use some.
Explaining the link in EMF in both sets of coil in the transformer are very common exam questions. The link in EMF in both sets of coil in the transformer are very common exam questions. Make sure you've mentioned every point, including the words change in flux, linkage, and induced EMF and induced current. You must be specific with your terminology for full marks.
Some terminology like the Faraday's law, right? Understand that? Okay, no problem.
Yeah, no problem.
Okay, so after we have learned the law related about the Faraday's law, okay, and let me explain the Lenz law. Okay, the Lenz law is help us to explain why the direction is opposite. Okay, the Lenz law is always used to predict the direction of the induced EMF in the coil or wire. Okay, the Lenz law is the induced EMF is set up in the direction to produce effect. The oppose. Okay, the oppose highlight. Okay, the oppose the change coordinate. Right. Understand it? So this is called the Lenz law, right? So the Lenz law is always used to explain the direction of the induced EMF, right? To explain the direction, right? Understand it? Okay, no problem.
Yeah.
Is there any problem about the Lenz law?
No.
What?
I said no. The microphone is back quiet.
Okay, so now you understand the Lenz law?
Yeah.
Or not? Okay,
Understand.
no problem. The Lenz law is always used to predict the direction, right? Okay, this is the usage. Okay. Look at the experimental evidence for Lenz law. Okay, and so to verify Lenz law, the only apparatus needed is the after the graph. Okay, then we need a bar magnet and a coil wire, a sensitive ammeter. Okay, a seal is not required. Okay, look at it. When the current diffraction, there's the induced current, right? Right. When there is the diffraction in the ammeter, right? There's the induced current, right? Okay, according to the diffraction of, so we use the diffraction of the ammeter to distinguish either induced EMF or not, right? Okay, and we use the magnets, the direction of the induced field oppose the direction the bar magnet is moving, right? Okay, when the magnet is moving into the coil, right? Into the coil, okay, they will produce at the beginning, okay, at this point, they will produce the current, right? Induced current, right? Okay, and when the magnet is leave out, okay, leave out of the coil, they will leave, and it's also the lambda, the induced EMF, the induced current, right? The induced current, the diffraction of the ammeter, right? In the ammeter, understand that? No problem.
Yeah, no problem.
Okay, look at it. A lone pole, either low source of the bar magnet, is pushed into the coil, right? Because this induces an EMF in the coil, right?
A known pole, either north or south of a bar magnet, is pushed into the coil. This induces an EMF in the coil. The induced EMF drives the current because it is a complete circuit.
The induced EMF drives a current because there's the complete circuit, right? Okay, so the Lenz's law indicate the direction of the EMF, and hence the current must be set up to oppose the incoming magnets, right? Okay, at the beginning, right? So, okay, so we'll produce the opposite direction, right? Right, opposing direction.
Yeah.
And since the lost pole approaches the coil face, the EMF must be set up to create and induce the lost pole, right? And this is because the two lost poles will rebel each other, right? Understand? Understand? Right?
Understand.
Okay, no problem. And after that, the direction of the current is therefore showing in the image above. The direction of the current can be verified using the right. Okay, no problem.
What's the
Which part? You don't understand?
right hand grip? The direction of current can be verified using the right hand grip.
Okay, the mic speaker a little bit terrible, and I can hear you clearly. So you can repeat. Okay.
Hello.
Okay.
I don't understand
Hello? Which part?
the right hand grip.
This one?
Yeah.
Okay, you don't understand this one, right? Okay.
Well,
The direction can be verified using the right hand grip rule. Okay, this the rule is called the right hand grip rule. The right hand grip rule is help us to distinguish the current and the magnetic density. Okay, the Fleming's law help us to distinguish the force always, right? And if we want to distinguish the magnetic field or the current, so we always use the right hand grip rule. Okay, I will draw like this. This is some like this, and this is the sum, right? And the other finger like this, right? If the density is upward, right? And the four fingers, right? The wrinkled, the like this, right? Okay, this direction is called the current. Understand that? Now?
Yeah. Okay.
Okay, so this is called the right hand grip rule. Understand that? Okay, so if the topic only tell us the current or only tell us the density direction, okay, so if we want to use the density direction to distinguish or to ensure the direction of the current, or use the current direction to ensure the direction of the density, okay, so we might use the right hand rule. Okay, so also called the right curl rule. It's a method to help us to determine the direction of the magnetic field produced by the current carrying wire or solenoid, right? Okay, understand that? The sum point up, the sum point in the direction of the conventional current or the density direction, right? Understand that? Your fingers will curl in the direction. Okay, remember, the fingers will curl in the direction, direction of the magnetic field line, right? Understand that? If the thumb pointing in the direction in the direction of the conventional, right? The current direction, right? Understand that? So now you understand the right hand grip rule now.
Understand.
Okay. So if we want to use a law, so we have to know one of the information. Like if you
Both ways.
got the direction of the density, so you want to distinguish the direction of the current, okay? Or you have known the direction of the current, and you want to use the information to distinguish the direction of the density, okay? So we always use the right hand grip rule, okay? As for the Fleming left hand, if we want to figure out the direction of the force, okay, so we always will choose the Fleming left hand rule. Understand that? So you know the difference between the right hand rule, grip rule, and the Fleming left rule. Now, understand that?
Yeah.
Okay, no problem. Oh, and after that, here is the law. Okay, this law is the Faraday's law. Okay, Faraday's law to calculate the EMF. Okay, the EMF value. Okay, if we want to calculate the EMF value, so we always use this formula. Okay, the formula is what? It's the rate change of the flux, right? The rate change of flux. Understand that? Okay, now. And here's the negative sign. Okay, the negative sign represents, according to lens law, which says the induced EMF is set up to oppose the change coordinate. Understand?
Okay.
Okay, no problem. Okay, so here is the law related about the Faraday's law, and another law is related about the lens law. Okay, the two laws help us to explain the EMF, induced EMF value, right? Understand it? The problem?
Yeah, no problem.
Okay, so here's the, and as for the Faraday's law, okay, the Faraday's law is only relate to the magnitude of induced EMF. Okay, induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, and there's no negative line. Okay, you must distinguish the Faraday's law and the lens law. Okay, the first law is only refer to the magnitude of the flux linkage, right? The rate of change of flux. Okay, and the lens law is only related about the negative, right? The direction. Okay, understand? The problem now.
Yeah.
Okay, look at that. And then combine the lens law and the Faraday's law. Okay, and the combining lens law into the equation for Faraday's law is written as like this one. Okay, this one. The negative sign represents lens law. This is because it shows the induced EMF is set up in the opposite direction to the opposite changing flux linkage. Okay, this equation also shows that the gradient of the graph of magnetic flux against the time, right? This is the rate change of flux, right? The rate change of flux represents the magnitude of induced EMF, right? No problem now. Okay.
Okay.
Okay, no problem. Okay, so here is the gradient of the graph.
The negative sign represents Lenz's law. This is Faraday's law. It shows the induced EMF is set up in an opposite direction to oppose the changing flux linkage. The equation also shows that the gradient of the graph of magnetic flux linkage against time represents the magnitude of the induced EMF. The negative sign means that if the gradient is positive, the induced EMF is negative. This again due to Lenz's law, which says the EMF is set up to oppose the effects of the changing flux linkage. I don't get it, but I'll remember it.
Of magnetic flux against the time, right? This is the rate change of flux, right? The rate change of flux represents the magnitude of the induced EMF, right? No problem now. Okay.
Okay.
Okay, no problem. Okay, so here is induced EMF, right? No problem now. Okay.
Okay.
Okay, no problem. Okay, so here is the for example. Okay, to finish the for example, how to do it? The topic one asks to copy the magnitude of the average EMF induced in the coil. Okay, how to use the Faraday's law and the lens law? Okay, no, not to use the lens law. Only use the Faraday's law to copy the magnitude of the average EMF induced in the coil. Okay, how to do it? Think about it. How to do it? The work example have the information like a small rectangular coil contains the 350 terms of the wire. The longer side is 3.5 centimeter, and the shorter side is 1.4 centimeter. Okay, so we got the area, right?
Okay.
Okay, and the coil is held between the poles of the larger magnets so that it can rotate about and access through the cylinder. The magnet produces a uniform magnetic field of flux density of 80 microtesla between the pole. The coil is positioned horizontally, then turned through the angle 90 degrees in the time of the 0.18 seconds. Okay, how to do it? Which formula that we use?
Use the magnetic flux formula first.
Yeah, no problem. How's the
So-
formula? This formula, this one.
Yeah.
So, and how to copy it?
So find the magnetic flux first. So 0.035 times 0.014 times 80 times 10 to negative 3, and then times 350
And then like this.
Yeah.
Okay, and take the known quantity into equation, right? Okay, into fraction, right? Okay, and final, and then we take the known quantity into it, and finally
Be
we get the answer.
negative.
Okay, you might need to calculate the answer, right? No problem now. Understand now?
What about the 90 degrees?
90 degree. 90 degree is the angle. It's the angle, and we want to find out the flux linkage, right? The flux, right? Okay, the flux is like the change, right? The change. At the beginning, the field lines is parallel, right? Okay, it's parallel to the coil, right? Okay, understand that? And now, and we through the angle of the 90, right? So they will become this, right? Understand that? Okay, no problem.
Okay.
Okay, so 90 degree has become the maximum area, right? Okay, so the change area, right? Just one area, right? The length times radius, right? No problem. The area, okay? The change in area, right? Because at the beginning there's no area, right? Because there's no any field lines across the area, right? At the beginning. Understand now?
Yeah.
Okay. And when we throw the angle of 90, okay, there's the maximum area, the magnetic field process, right? Okay, so the change, right? So from the beginning to the rotation of the 90 degree, then we got the change, right? Understand now? Okay, no problem. So we calculate the area, okay, the change area. Okay, no problem. Okay, and take the lone variable, the lone the quantity into the fraction, right? Understand that now?
Yeah, okay.
Okay, okay. So this is today's physics lesson that we have learned. Okay, and quick review it. And in today's lesson about the physics, okay, we have learned the length law, the Faraday law, and how to calculate the process and describe the process, right? And the change of flux, right? And the equipment induced EMF between the link the coil. That is the transformer, right? Understand that?
Yeah.
No problem. And we have learned, okay, the induced EMF, okay, the every process, okay, when it change, and we have learned how to distinguish the Fleming's left hand and the right grip hand, right? Roll. Understand that?
Yeah.
No problem. Okay, okay. So let's continue to talk about the mass. Okay, the mass. Hello, can you hear me?
Yeah,
Okay.
hello.
Um, okay, you can see what we have shared.
Yeah. Well, wait, I didn't send you the homework yet. I finished all the question
Mm,
except for the last one.
okay, and for the so you can just to see the answer you choose. Uh-huh. The is that sex, right? Choose what?
Wait, let me check. Number two is A.
Okay, the number two, the scalar quantity, right?
Yeah.
You choose the one, the A charge, right? No problem. Okay, and the sex, choose what? The capacitor. Okay, the sex, you choose what?
I choose C.
C, right? Why C? Why do you choose C?
Because on P is the positive charge, on
Mm-hmm.
Q is negative charge, so it's P to Q.
Okay, no problem. Okay, and the seven, right? Seven, you choose what?
I chose B.
The answer B. Why the answer B? The answer B is right. Why?
Uh,
Why the B? Decrease the decrease in the distance between the two plates increase, and the capacitance of the two parallel plates. Okay, here's the two parallel plates. Okay, just the graph, right? The same graph. Okay, because the question 6 and 7 refer to the information below. Okay, and the separation it decreased at the time x, right? So when I decrease the separation, what quantity that will change? Mm-hmm.
uh, the capacitance increase.
And how's the current change?
I think current increases because
Mm-hmm.
uh current increase because the charge increases.
Okay, at the initial condition, right? If I increase the separation of the two parallel plates, okay, so then we can use the formula related to the capacitance, right? The C equal the A and it's 4 pi, right? 1 over D, right? Understand this formula, right?
Yeah.
Related to capacitance. Okay, so if I decrease the separation, so I change the D, right? Okay, decrease the D. So the C that will increase, right? Okay, now the C that will increase. If the C increase, the capacitor that will charging, right? And the ammeter that have the current, right? Okay, understand that? Mm-hmm. So the current will increase, right?
Okay.
The current will increase, right? Okay, no problem. So the point, the X, that have the increase, right? Okay, and the Y, at the time Y, the separation become constant. Okay, if the separation become constant, so the C constant, right? If the C constant and the current the constant, right? Understand?
Okay. Yeah.
Okay, and the next, the topic is the eight, right? So you choose what?
I didn't know how to do.
Okay, look at it. The initial potential difference, okay, so we call it the V zero, right? And the capacitor is discharged. Now the capacitor is discharged through the resistor. Okay, so in the process that we are discharging, right? Discharging the energy, right? Which means the capacitor that will release the electrical energy. Okay, and the potential difference across the capacitor decreased too. Okay, in 2 milliseconds, the time. So we got the time interval, right? Understand that? The time interval, the
Oh yeah.
time is what? Is what? It's
2 millisecond.
2 millisecond, right? Which means the 2 times the -3, right?
Yeah.
Okay, second. And so the potential across the capacitor decreased to. Okay, what is decreased to? So the remaining potential is what? Decreased to. Mm-hmm. What is the capacitor decreased to? Decreased to without the over 3, which is means what? Mm-hmm. Means the remaining voltage, right? Remaining voltage is without the over 3. Understand that?
Yeah. Okay.
Okay, so which formula that we can use to calculate the time constant? Mm-hmm. Which formula that we can use? Discharging, right?
Oh. Okay.
Discharging formula relate to relate to voltage, right? Okay, have you ever remember this? And the remaining voltage, right, equal what? And the initial voltage and times what? The E, the negative T over RC, right? The RC is the constant, right?
Yeah.
Understand that?
Yeah. Yeah.
Okay, and here we know the remaining voltage, right, is what? Is the V delta over 3, right?
Yeah.
Understand that? So we can cancel this one. So we can get the 1 over 3 equal the E negative T over RC, right? And we also know what quantity. Hmm?
At the time.
Okay, the time interval, right? Okay, so we're going to take the time interval into equation, right? To solve what? To solve the RC, right? 1 over 3 and equal negative 2 times the negative 3, okay? And over RC, right? Okay, and you can use the calculator, right? To try to calculate. Understand that? Mm-hmm. How to? So in this step, how to solve the equation to get RC? Mm-hmm. How to solve equation?
Uh, ln 1/3 equals -2 times 10 to -3 over RC.
So can we choose side use the log x, right?
Yeah.
So okay, and this one we got the log, right? The log. Okay, this one and the right side is the negative, right? Log. Okay, the 2 times over -3 over RC, right? Oh, so we can simplify, right? The right side is what? It's -2 and times what? And over RC, right?
Yeah.
Okay, so here this one is negative log 3, right? Okay, understand that? No problem. Mm-hmm. And we can cancel the negative, right? So
Yeah.
got
Cancel the negative.
the log 3 is what? The 2 times the 10 and -3 over the RC. And the separating variable and RC equal 2 times -3 over log 3. Now we get the answer. Understand that? No
Okay, I
problem.
understand. Yeah, I see it.
Okay, so this is the final answer. Okay, no problem now.
Yeah, it's good now. Yeah.
Okay, but the answer you can see the final answer that we choose the B. Okay, why choose the B? Because we didn't we didn't transfer the in the formula we didn't transfer the time unit because the time unit the topic they used still use the millisecond, right? So we don't need to transfer the time into a second, right? Also use the 2 millisecond. Okay, understand that?
Okay.
Okay, because the topic still use the millisecond, not the second. Okay, so we don't need to transfer the unit. Okay, so the final we get the option B. Okay, understand that?
Yeah.
Okay, so we quick to reviews what formula that we use and what the known quantities that we know. Look at that. The topic, the first we read, the remaining, right? Decrease 2, which means the remaining, okay? Understand? The decrease 2, which means the inner discharging process. And the remaining potential is what? Is this one, okay? Remaining, okay? Understand that? And we also got the time interval, right? Okay, so we have to know the remaining potential and the time interval. Okay, and we want to get the variable time or constant. Okay, so first we have to remember this formula. This formula, discharging, right? Discharging relate to the potential. Okay, understand that?
Yeah.
And we take the known quantity into equation, right? So we got this equation, okay? And then we use the two-side lowering, right? Using two-side lowering x, right? Okay, and we also finally we got the answer, right? Understand that now?
Yeah.
No problem.
No problem.
Okay, and the next question is what? Mm-hmm. Is is what? Is the 14, right? Okay.
Yeah.
Okay, look at that. Okay. The first, to draw the electric field around the negative. Okay. How to draw the negative point charge? The point charge relate to the negative. Mm-hmm.
Lines from infinity towards the center.
Okay, no problem. Okay. You probably might draw the six, right? Six field line, right?
Oh, yeah.
Also, you normally we all draw the six to understand it. Okay, no
Okay.
problem.
Yeah.
And look at this one. When a bee get close to the flower, then it can detect the electric field. Okay, and the charge on the flower acts as the point charge at the center of the flower. At the distance, okay, we have known the distance from the center of the particular flower. The potential is negative, okay, and the potential, okay, away from the center, the potential is the negative 16 voltage. And we want to show that the charge on the flower is negative, the one a nano charge. Okay, and you how to do it?
I
How to solve the
use two equations.
what equation?
First one is charge over 4 pi permittivity of free space times r squared, and the other is uh
Because the object in the topic is the charge point, right? So we want to calculate the potential, right? So we use the q, the charge over 4 pi epsilon, right? Okay, and times what? The the
r
distance,
squared.
the r square, not r square, the r,
Oh,
uh,
oh,
not r square, the r. Okay, the formula. Okay, and to take the variable and q, so also q equal what? The v times the 4 pi, right? Epsilon and times the r, right? Okay, understand that? No
okay.
problem.
Yeah, yeah.
Oh, and finally we take the quantity into equation, and the v is negative. It's negative 6, negative 16. Okay, and times 4 pi. Okay, and here's the epsilon. Okay, here's the epsilon is what? It's 8.85 and times the 10 and negative 12. Oh, 12, okay, and times what? Radius, okay.
Yeah.
Finally, we can got is the probably the answer is the negative 1.07 times the 10 and negative 10 charge, and the final answer approach to the this one. Okay, understand the process, the detailed process. Okay, understand now. Remember this one equal this one. Okay,
Yeah.
no problem.
No problem.
Okay, and how about the question 2 of the B? You have to do it.
Calculate the electric field strength.
What?
Calculate the electric field strength.
Calculate. Okay, and deduce. And so we want to deduce whether the suggestion is correct. So first you have to answer the question. The suggestion is the correct or not. Make the conclusion first step. Understand that? First, we need to make the conclusion. Okay, so the conclusion to represent the suggestion is the correct or not. Okay, so you think the suggestion is correct or not? Mm-hmm.
Is incorrect.
Okay, so the incorrect. Why? Mm-hmm.
Because when you calculate using the radius, you get um 89.9, which is smaller than 120.
Okay, and we can use the electric field strength, right? The formula, the Q over what? Over 4 pi, right? The 4 pi epsilon and times the radius square, okay? Understand at what? At what? At 10, right? At 10 centimeter, right? 10 centimeter. Okay, to calculate, right? And take the 10 centimeter into equation, right? So we got the Q over 4 pi epsilon and times transfer unit, the negative 1. Okay, the 0.1 square, okay? Understand that? The finally,
Yeah.
we can get electric field strength at a distance, the center, the 10 centimeter, okay, is the approximately use the calculator to calculate. And the final result approximately the 96 voltage per meter, okay? And we found the result answer and less than the 120, right? Understand that? No problem.
Uh,
So finally, we can get the conclusion is incorrect. No problem. Because in the B, we need to answer the B cannot, right? Cannot detect, cannot detect at 10 centimeter, right? No problem. Understand that?
when I calculate, I get 89.9.
You got 89.9.
Yeah.
Why 89? You use the calculator to calculate it, right?
Yeah.
And the Q. So you Q, so you use the what? Q. This
0.1 times 10 to negative 9.
mm, and this one, you use what?
0.1 times 10 to negative 9.
Okay, and you got the answer. You
Negative
got
1.
okay. So finally, you use the calculator, get the answer. It's not the 96, right?
Yeah.
It's what? It's what?
89.9.
It's 89, right? Okay. So it's also less than the 120, right?
Yeah.
Okay, no problem. I didn't use the calculator, so I can sure what is the exact value. I guess probably because I can use the cell phone to calculate the pi, right? Okay, and you use the calculator to get the real answer is the 81, and the 81. So we use the 81 to compare with the 120, and we found out the 81 is less than 120, right? And
Yeah.
we make conclusion is the suggestion is incorrect because the B cannot detect at 10 centimeter. No problem now.
Yeah. No
Okay.
problem.
Okay, and look at the mark, right? The here mark is 3 marks. Okay, first 1 mark is for the conclusion, and 1 mark for the formula, and 1 mark for the value. Okay,
Okay.
and the question C, it is suggested that here's on the B deflect. Okay, deflect slightly when close to the flower, and the topic want us to explain what would cause the here to deflect in the electric field. Okay, how to answer the question?
I wrote that there is static charges in the hair.
Mm, is it static charge in the here, right?
Yeah. Static charges.
Okay, and then because use the static charge, and then
They experience a force in the electric field.
okay, so like the electric field, and
They experience a force.
okay, so what personal force, right? The electric force, right? No problem.
Yeah.
Okay, no problem. Here's the answer divided into the this one. If your answer relate to the electric force, so we can get a 1 mark. Okay. And another mark is for the static charge. Okay, because static is the electric field. Okay, understand that now.
Okay.
Okay. And the next question is that is 17, right? Okay, it's 17. The Q1, I only just want to explain the Q8, right? Okay, the rest of it don't need to answer. Okay, and the question A want us to explain why the aluminum disk rotates in the same rotation as the magnets. Okay, the mark is 6. Okay, how to answer the question? And you how to answer the question? Mm-hmm. You how to answer the question? Mm-hmm. Look at the topic. The diagram shows a section through the component of the speeder speedometer for a bicycle. Okay, the front wheel X of the bicycle is connected to the cable. The cable rotates. Okay, the cable rotates as the bicycle wheel rotates. The other end of the cable is connected to the magnet. Here's the magnet. So we probably may think the magnetic field, right? And the magnetic force, right? Okay, maybe the Faraday law, maybe the Lenz's law. Okay, understand that? Mm-hmm.
Uh. Okay.
Okay, and the aluminum disc is shaped so that it is close to, but not touching, the magnet. The disc is connected to the pointer by the shaft. A spring prevents the disc and shaft from the freely rotating. Okay, look at the equipment. Okay, look at equipment. And how to explain why the aluminum disc rotates in the same direction as the magnet. Okay, the same direction. Why? Why have the same direction? Use which laws that we might use in the magnetic chapter to answer the question. Mm-hmm. You have used some law to answer the question. Your answer is what? Your answer is what? Hmm?
This one I didn't answer.
Oh, you didn't answer, right? Why?
Uh, I didn't have time.
Okay. And after we read the topic, okay, and because we have seen there's the magnet, right? And the cable rotate, right? And there's the magnet and the cable rotate, right? Okay, you look at the graph, okay. Here's the rotating magnets. Okay. And when it comes to the rotating magnets and their axis, so we might think they probably produce, right? They probably produce the current, right? The induced EMF or the induced, right? So we probably may think they may produce the induced EMF, right? Okay, or the current, right? Understand that? Understand
Yeah.
now?
Okay.
Okay, if you produce the induced EMF, so we might use the Lenz-Thor or Freddy-Thor, right? Lenz-Thor or Freddy-Thor, Freddy, Freddy-Thor or Lenz-Thor, right? Use the Lenz-Thor. Use Lenz-Thor to answer. Okay, and look at equipment. The first, because the wide alumina disk rotate in the same direction as the magnets. Okay, rotates in the same direction as the magnets. So mm, ro rotating. So because the rotating causes the charging magnetic flux through the alumina disk, right? So the first step we need to answer the rotating, the rotating magnet. Okay, because the most rotating magnets cause cause what? Cause what? Cause changing, right? Because rotating, right? Changing what? Magnetic, right? Flux through the look at it through the disc, right? Along the disc. Understand now?
Okay.
Okay. If the rotating magnets cause the changing magnetic flux through the aromatic cell might produce what? Produce what? Produce what? So might produce what? Mm-hmm. Which produce EMF, right? Will produce what? Produce the induce, right? Because there's the changing magnetic flux through the alumina, right? So which will produce the induce, the induced EMF, right? And what? And the current, right? In the disk. Okay, understand? Understand?
Okay.
Hello?
Yeah, yeah, yeah.
Okay. So the first step, because there's the rotating magnet. Okay, because rotating magnets cause the changing magnetic flux to along the disk. And this process will produce the induced EMF, okay, and the current in disk. Okay. And so we can use the lens law, using lens law by lens law. Okay, by lens law. By lens law, the current, so the current, the experience magnetic, right? The magnetic force, right? The force that follow that follows the magnet. Understand that? Mm-hmm.
Okay.
Right? And a disk, and then this rotates same direction, right? No problem now. Mm-hmm. Understand? Okay. Look at it. Understand what I write.
Yeah.
Okay. And I need you to tell me in this the 17th topic, what tell us the word and what laws that we might use in the topic to explain why the aluminum disk rotates in the same direction as the magnet. Mm-hmm. Mm-hmm. Think about the topic want us to explain why aluminum disk rotates. Rotate. Rotate the same direction as the magnet. Okay, you look at the equipment. You look at the equipment. Equipment. You think about when the if when the magnet, okay, when the magnet rotates, and it will create changing magnetic flux through the aluminum disk, right? Okay, and we have learned the Faraday's law of electromagnetic induction, right? And we know the changing flux in the changing flux that will induce current in the disk, right? No problem. Understand that? Mm-hmm. So we can use the lens door to explain the current and produce a magnetic field. Okay, the magnetic field that produce a magnetic field that opposes the change in the flux, the causing, right? This is the lens door. Okay, because lens door tell us the current. Lens door tell us the current that produce a magnetic field. Okay, magnetic field and that oppose. Okay, the oppose the change, right? The oppose the change in flux, right? And the flux that cause them, right? Understand? Mm-hmm. The problem. Mm-hmm. So this means the induced magnetic field interacts with the rotating magnet, right? and creating a force. Okay, so creating a force, the force that tries to follow the magnetic motion, right? So thus we can get the conclusion, right? The disk rotates in the same direction as the magnets. Okay, understand now? Hello?
Yeah, yeah,
Mm-hmm. Can you hear me?
yeah, yeah. Hello?
Okay, and I want you to tell me how to explain the equation. You can tell me which laws that we might use in the equation, in the topic. Mm-hmm. From the graph, what laws that we might use to explain why the alumni disk rotates in the same direction as the magnet? Think about it and tell me which laws that we might use from the graph and the words the topic tell us to explain it. Mm-hmm. Think about it and tell me.
Use the lenses law.
Okay, why we use the lens law? Because there's what? There is what? There is the changing flux, right? Magnetic flux, right?
Yeah.
Because there's the changing magnetic flux through the aluminum disc, so we might use the induced EMF or induced current, right? Because there's the closed circuit, right? The closed. Okay, so we can use the induced current. So use the induced current that we can use lens door. Okay, the lens door tell us if the current produces the magnetic field, the opposite change in the flux, the cause then, right? The cause then. Okay, understand now?
Okay.
Okay, so this is the assignment I sent you to you, and look at the today we're going to continue to learn. The last lesson we have not induced EMF, right, through the coil, right? And we have observed some the diffraction in a deflection, the current in the emitter, right? Okay, and we also know the factors that increase the induced EMF are, right? This one, understand that?
Yeah.
Mm-hmm. These are factors that will increase the induced EMF. First is the magnets move faster, okay, and the inducement is greater, okay. And the second is adding more turns to the coil. And third is increasing the strength of the ball magnets. Okay, no problem. Understand now?
Yeah.
And another one is the between the linked coil is the transformer, okay. And I have to tell you the transformer is being used to pass through a long distance current. Okay, so a transformer is a device that works by the principle of the electromagnetic induction. Okay, and it changes according to the alternating voltage and no current to no alternating voltage, a high current. Okay, and the transformer is made up of the one is the primary coil, the second is secondary coil, and the third is the iron coil. Okay, look at the equipment. No problem now. Understand that the transformer. Okay,
Okay.
okay. So I need you to tell me, the transformer is what? And we usually use transformer to what? To do what?
To transmit the EMF,
Yeah.
it has alternating current from the
Yeah.
primary coil to cause another alternating current in the secondary coil.
Okay, no problem. And what is the transformer made up of?
There's primary coil, secondary coil, and the iron core.
Why we choose the iron core?
Because it is easily magnetized and demagnetized.
Okay, no problem. Okay, and so here's the loss that we might use. If there is a changing magnetic field passes through the secondary coil through the iron core, right? And this resulting a changing magnetic flux linkage, right, in the secondary coil. So, and we got the Faraday's law. Here is the EMF induced, right? No problem now.
Yeah.
Okay, and look at it. If there's the EMF produced according to the alternating output voltage from the secondary coil, okay, and this one, right? And we have to do the work example, and we describe the when the switch on and when it remains on and when the switch off, okay, and the different formats that we got a different answer, okay. You remember that?
Yeah, I remember.
Okay. Look at this one. Okay, and here's the exam tip that I want you to remember. When we explain the linking in the EMF in both sides of the coil, okay, and we need to use the Faraday's law, okay, when there's the any magnetic electromagnetic flux linkage, right, and we might use the Faraday's law, okay. Understand now?
Yeah.
Okay, and look at the induced EMF. So I need you to tell me what is the induced EMF and the condition if we want to produce the induced current. The condition is what? If we want to produce the induced EMF, what is the condition? And also further, and I also want to get the induced current, and the further condition is what?
Closed circuit.
Yes, because the closed circuit, right? If you have the when you produce the induced EMF, okay, and the further condition is if we have the closed circuit, okay, and we also can get the induced current, okay, no problem now. Okay, and here's Lenz's law. Okay, the Lenz's law is used to explain the direction, right? Because the previous topic that want us to explain the direction, so I use the Lenz's law. Okay, understand now? The Lenz's law is what? The Lenz's law is all is used to predict the direction of the induced EMF in the coil or wire. Okay, and induced EMF is set up in the direction to produce effects, the oppose. Remember the word oppose. Okay, understand that? Oppose. Why the oppose? Mm-hmm. Mm-hmm.
Because of the Lenz's law.
Actually, it because when we induce the EMF, okay, and the change in the flux, they produce the force. In the magnetic force that will oppose the motion, okay, and in the lens door. So oppose the motion, which means they have the effect that oppose the changing coordinate. Okay, no problem now.
Okay.
Okay, and look at experimental evidence for lens restore. Okay, and in the lower, okay, and I want in the lower we the purpose to verify the lens store. Okay, that use the apparatus is the bar magnet. Okay, and the very beginning we put the magnet into the left side, and when the coil move in the coil, right? Move, yeah. When the magnets move in the coil, okay? Okay. At first, the direction of the induced field opposes the direction the bar magnet is moving. Understand? So we will find the bar magnets induced current in the wire have a diffraction, okay? A diffraction is to the right, okay? And when the magnets leave from the coil, okay, and we found also the current, okay, the current in the diffraction ammeter, okay, the ammeter have the direction to also is the right, okay, and according to the observation, and we concluded the laws of the lens door, okay, the lens door tell us the direction of the current, the direction of the current, okay, a direction of current use the lens door to indicate the direction, okay, this one, the direction of the EMF and hence the current must be set up to oppose, remember, oppose the incoming magnets, right? And since the lost pole approaches the coil face, the EMF must be set up to create an induced lost pole, right? This is because the two lost poles will repel each other. Okay, understand now?
Okay.
Okay, and look at it. If I reverse the magnetic direction, okay, that we gave an opposite deflection, right, on the voltmeter. According to lens law, the lens law now predicts as the south pole induced at the coil entrance, right, and this will attract the lost pole attempting to leave, okay, and therefore the conclusion is the induced EMF always produces effects to oppose the changes causing it. Understand now?
Yeah.
Okay. And finally, and remember this, the lens law is the direct, okay, the lens law is the direct consequence of principle of conservation of energy. Remember? Mm-hmm.
Yeah.
This one.
Okay.
Okay, remember this one. The lens law is the direct consequence. The lens law is the direct consequence of the principle of the conservation of energy. Understand now?
Yeah.
Okay, remember that. Electromagnetic effects will not create electrical energy out of nothing. Okay, so from the one form of the energy to another form of energy. Okay, and remember this one, electromagnetic effects will not create electrical energy out of nothing. Okay, understand that?
Okay.
So in order, if we want to induce and sustain an EMF, for instance, so the work must be done, like overcome repulsive effects due to lens door. Okay, and remember this one, the formula that we use to calculate the EMF value, the magnitude. Okay, the denominator is a change in the flux linkage. The denominator is the time interval, right? Here's the negative. The negative represents the direction. The direction is according to the lens door. Okay, understand now the problem?
Yeah. Okay.
Okay, let's continue. Okay, here's the Friday slope. Okay, this one. Remember this work example? Mm-hmm. Okay, Look at the work example. The last lesson we have talked about this one, okay? And you asked me what is how we use the angle of the 90 to calculate the average, the EMF induced in the coil, right?
Yeah. Yeah, yeah.
Okay. And I want you now tell me in the topic the which laws we might use to calculate the average EMF induced and what is the value of the magnetic flux linkage is what? I want you to tell me. hmm What is the flux? The magnetic flux linkage is what? According to the topic, the flux linkage. Okay, the change in the flux linkage is what in the topic? In this
EMF.
topic. Okay, now if the flux linkage over the time, that the rate change of the flux linkage is the EMF. Okay, understand that? The change, okay, remember, change in magnetic flux linkage. Okay, the linkage is the N times the delta phi, right? Understand? It's one. Okay. If you want use this one to calculate the EMF, okay, so we can, which is the rate change of the rate of the rate change of, okay, the linkage, okay, which equal the N, the delta phi over what? Delta T, right? This is the EMF. Understand now? Okay.
Okay.
Now
Okay.
compare difference, the rate change of and the change of. Okay. Understand now. No problem.
Yeah.
Okay. And look at it. Okay. And here's the alternating current and the potential differences. Okay. And the last chapter we have learned the alternating current in a transformer. And alternating current is defined as the current which will theoretically varies between the positive and negative. Okay, like this. If I change the current and periodically from the positive to negative, okay, and this form, we can call, understand that? We can call what? The alternating current, right?
Right.
Okay, and because the alternating current has a period, okay, and we use this one, okay, this one, the frequency to calculate the period. The period is a reciprocal of the frequency. Okay, the unit related to the frequency is the hertz, and the unit of the period, time period, is the second. Okay, no problem now.
No problem.
Okay, okay, look at it. This one, look at the graph. Okay, there is a single graph related to the voltage, the current. Okay, this is the alternating current, abbreviation AC. Okay, and we can see from the graph the current magnitude the changes from periodically, okay, from 0, and the period is the 20 millisecond, okay, no problem now. So from the graph we can read the period, okay, and we also can read the maximum magnitude of the current, which is called the peak current. Okay, this is the maximum value, right, of the current. No problem.
Yeah.
Okay, and look at that. According to the alternating current against the time graph. Okay, so after we read the period, the maximum value, okay, and we want to calculate the word is mean is the row mean square current voltage. Okay, and remember the row mean square, the value of current or the voltage, and is the usual way of comparing AC current or voltage, and it's the equivalent direct current of the voltage. Okay, we know in a long distance, the AC transformer transforming the electrical energy, that we might lose the thermal energy, right? Understand that? So we have the heating effect. Okay, and the power will dissipate, right? And so finally the remaining energy or the remaining current, the remaining voltage have the relationship with the maximum value of the alternating current. And we call the final the rho mean square. Okay, the rho mean square is defined as the equivalent direct current that produce the same power. Okay, understand? It's one. No problem. Mm-hmm. Hello, can you hear me?
I'm thinking right now.
Okay,
Okay, yeah.
okay. Actually, the rho mean square current is the voltage is the remaining voltage or the remaining current after if we use the transformer to long distance electrical energy passing, right? And in the process, we have the heating effect. Okay, and a part of the power will dissipated. Okay, and finally the remaining the electrical energy, the current, the voltage. Okay, we call the roaming square current or voltage. Okay, and the roaming square is equal to okay the 0.7, approximately 0.7 times the maximum value of the current. Okay, the I zero is the maximum value. Okay, the maximum value, the maximum current. Okay, understand that, which is about 70 percentage of the peak current island. Okay, understand that.
Yeah.
Okay, and from a graph, we can use the line to represent the seven 70 percentage. Okay, use the horizontal line, this one, the rooming square voltage. Okay, or I can change the voltage into the current. Okay, so this is the rooming square current. Okay, this is the approximately the 70 percentage. Okay, which is means in the process the long distance passing the electrical energy. Okay, the transformer the process, and we have dissipated the 30. Okay, or might say we lose the 30 percentage of the energy. Okay, the energy is the thermal energy. Okay, and the remaining the 70 percentage. Okay, understand now? Okay, understand now?
Yeah.
Okay, and here's the formula. Okay, the formula relay about this graph. Okay, and look at the graph. Look at the work example. Here the graph is the voltage versus the time graph. The variation with the time of the output voltage V of the alternating voltage supply is shown in the graph below. Okay, so the topic want us to use the graph to calculate the frequency of the supply and the peak voltage. Okay, so How to use the graph, the information from the graph to calculate the frequency of the supply and peak voltage. Okay, the frequency. Okay, how to get the frequency from the graph, or might use some info, some laws, some formula. Mhm.
Find the time period.
Time period. Okay, what formula? Mhm. Frequency equal what? Have any relationship to the time period?
1 over time period.
Yeah, because frequency is 1 over period. Okay, and the period can get from what? From which part? From the graph. Mm-hmm.
Uh, 0,
The period,
0.2.
because in the period this one, right?
Yeah.
This one, 0.2 and the millisecond, right? Okay, this is 1 over 0.2 and times, right? And 10 negative 3 second, okay? Understand it? So finally we can get the frequency, okay? And the peak voltage, okay? The peak voltage is what? From a graph. Mm-hmm. From a graph. The peak voltage is what? From a graph.
17.5.
Approximately, uh, probably approximately 17, right?
Yeah.
0.5. Okay, no problem. Okay, so if I want to get the Roman square voltage, okay, how to get the Roman square voltage from the peak voltage? Now, if I got the peak voltage is the 70.5 voltage, right? And I also want to get the Roman square voltage. Okay, I want to get the Roman square voltage. Roman square voltage. Okay, equal what? Mm-hmm. I have known the V max is 17.5, and I want to get the Roman square voltage. Okay, is there any relationship between the Roman square and Roman square voltage and the maximum voltage? Mm-hmm.
Not sure.
Okay, look at the formula, and I have to tell you, the roaming current is equal to the 70 percentage of the peak current, right? So also the same law apply for the voltage, right? So the roaming RMS, the voltage equal the 70 percentage of the peak value of the voltage, right? Understand that? This one? Okay.
Yeah.
Okay. And the rho mean square current equal the what? The 70
70%.
percentage of the current, right? The maximum current. Okay. And the topic, we have lowered the maximum value of the voltage is 17.5. Okay. And for the rho mean square voltage is the we use the 70 percentage, right? And times the 17.5 voltage, right? So finally we can get rho mean square voltage, right? No problem now? No problem
Yeah.
now? Okay, this one. And here's the formula. Okay, the formula. If I want to get the rho mean square current and the potential, okay, the rho mean square is what? Okay, the rho mean square, the current that we use the initial value, the maximum value, this one, the maximum value, this one. 2 over square root 2. Okay, because the square root approximately is the 0.5. Okay, it's a 70%, right?
Okay.
No problem. Okay, so we use this law. The first law it help us to calculate the row mean square current. Okay, the second law is help us to calculate the row mean voltage. Okay, the relationship between the maximum voltage and the row mean square voltage. Okay, and look at for example, and the for example tell us an electrical oven is connected to a 230 voltage row mean square. Okay, here's the value is the row mean square. Row mean square means the supply using the cable of negligible resistance. The now the topic want us to copy the peak to peak voltage of the mains supply. Okay, so tell me what is the maximum value of the voltage? Is what? Use the previous formula above. Mm-hmm. How to solve the equation? How to solve the work example?
The times root 2.
What?
Times root 2.
Square two, right?
Yeah.
The 220 is what? Is the Roman square, right?
Yeah.
Okay. And so the 230 equal the maximum value, okay, over the square root 2. Okay. Understand now?
Yeah, yeah, yeah.
Okay. And this one, so we got the maximum value of the voltage is the 200 and times the square root 2. Okay, no problem now. Understand now?
Understand.
Okay, look at it. Oh, this one. And look at it. Remember. Okay, remember the Roman square value in the AC circuit is equal and equivalent to the value of the current and the voltage that produce the same heating effect in the DC circuit. Okay, understand? So, which means we can use the rooming square value in a circuit for equivalent calculation involving the DC circuit. Okay, understand now? No problem now.
Yeah.
Okay, so this is today's lesson, the fifth lesson. Okay, let's come to the math lesson. Um, the remaining math quizzes you have done, you have finished, you finished. Mm-hmm. The question 9 to the 11, you have finished.
Not yet. No.
Why?
Just a bit tired.
Okay, look at this one. Let's continue to explain every single topic. Look at the line. Okay, the topic tell us there is the uniform ladder. Okay, there is the uniform ladder of and the weight W rests in equilibrium. Rest in equilibrium with one end and one rough horizontal. Here's the rough horizontal ground, and the other resting against a smooth vertical wall. Vertical wall. Okay, and the vertical plane containing the ladder is at right angle to the wall, and the ladder is inclined at 60 to the horizontal. Okay, and we also know the coefficient of friction between the ladder and the ground is the U. Okay, the first question want us to, in terms of W, and to calculate the value, the magnitude of the force exerted by the wall. on the ladder. Okay, how to solve this topic? How to analyze? Mm-hmm. Can we sketch the graph?
Oh, yeah, yeah.
Okay, here's the ground, and there's the wall. Okay, there's the wall. Okay, and here's the ladder, right? The problem.
Okay.
And this is the angle is the 60. Okay, and the friction is the U, right? Coefficient. Okay, and mm, okay, no problem now. This is ladder. Okay, first we need to analyze which force that exerted on the ladder. Okay, first let's analyze this point. Okay, which force? Mm-hmm. Which force? Mm-hmm. It's a normal reaction,
Right.
right? Called R. Okay, here's the weight, right? Mm, and how about the friction?
Is to the left.
Okay, the friction. Okay, okay, friction. And in the vertical, right? The vertical. Okay, the vertical is in the equilibrium, right? The vertical equilibrium. So we can use the vertical equilibrium to establish the equation, right? Okay, how to use the vertical equilibrium, the condition to establish the equation. In the vertical direction, which force is only R, right? Upward, right? Is up.
Yeah.
And the weight is down, right? So
Yeah.
the R must equal the weight, right? Okay. And second, after we have used the vertical equilibrium condition, okay, and we also use the moment, right? Take a moment, okay? Take a moment. So we can take a moment. Um, and I suppose the length of the letter is L, right? Okay, so take a moment about the base. No problem. About the base of letter, right? Okay, no problem now. Okay, understand. Here's the weight section. Okay, no problem now.
Okay.
There's the normal action from the smooth wall, right? There's
Yeah.
the smooth wall. Here's the normal action. And I suppose the S. Normal reaction. Normal reaction. Mhm. Smooth. Okay, smooth wall, right? No problem now. Okay, so if I take the moment about the base of letter, okay, so we can establish the equation, right? Because the letter now is equilibrium, okay? Equilibrium, which means what? Which means what? Which means the clockwise, right? The clockwise moment equal what? Equal what? Equal what?
Equals the anti-clockwise.
Yeah, the anti-clockwise. Okay, so now analyze the clockwise moment. Which force that produce the clockwise moment? Which force that will produce the clockwise moment?
The normal on the smooth wall.
Okay, and the normal. So we can use what? If I take this one, if I take this point, it's the pivot, right? Okay, so when got the clockwise moment is the force, right? The normal force, okay? The problem. So it's the force times what? Length. The length of the ladder is L, right? Okay, so here's the angle of the 60, right? And I want to got this one, right? Problem, right? Okay, the length from the normal reaction from the smooth wall to the ground, the length is L times the sine, right? Okay, no problem now. So the clockwise moment is the S times L sine 60. No problem. Okay, understand that. Okay, right?
Yeah.
Okay, and for the anti-clockwise, okay. So which force that will produce the anti-clockwise moment is the weight, right? It's the weight. Okay, so the weight that will produce the anti-clockwise moment. Okay, here's the weight. Here's the weight W, and we want to calculate the distance, right? Is horizontal, right? Okay, this length is the top of the ladder. Okay, so we got horizontal part. This one is the L over 2 times what? Is the cosine 60 degree, right? No problem now. Okay, and this is the weight.
Why is it
Okay,
cosine? Why is it cosine?
because the horizontal part. Okay, the perpendicular is horizontal part because the weight is the downward, right?
Yeah. Oh, I see. Okay.
And so W times what? The horizontal part is the L over 2 and times what? Times cosine 60, right? Okay, so we got the equation 2, okay? And we can cancel L, right? Cancel L. So we got the the S times 60 sine 60 equal the W times the 1 over 2 in the cosine 60. No problem now? Okay, understand it. No problem now, understand it. And we take the value, okay? The S times sine 60 is the square root 3 over 2 and equal the W times 1 over 2 times sine 60 is 1 over 2. Okay, over 2. So we got the relationship between the W and the normal reaction for the smooth wall. Okay, so this S equal the W over double square 3, right? No problem now. Okay, understand it. Okay, the topic.
Okay.
Okay, so we have finished topic 1. Okay, in terms of W, to calculate the magnitude of the force exerted by the wall on the ladder. Okay, okay, so have got the 6 marks. Okay, the second question, want us to show that the coefficient is greater than and equal the square root 3/6. Okay, so we have to establish another equation. Okay, another equation. If I want to show that the coefficient is greater than and equal to square root 3/6, okay, so we can use, after the question 1, we have to use the vertical equilibrium, okay? And here now, and we can use the horizontal equilibrium, right? Horizontal equilibrium. Okay, understand? Okay, and in the horizontal part, okay, which equation that we can establish? Horizontal is only force and the normal reaction from a smooth wall, right? So the friction equal, right? Equal the S. Understand that? No problem now.
Yeah.
Because the direction of the normal reaction from the wall is the right direction, right? Horizontal right direction. And the friction is the left direction, okay? According to horizontal equilibrium. So we can got the friction equal to S, right? No problem. Okay. And we can use the friction equal the coefficient times the normal reaction R, right? And equal to S. No problem now. Okay. Understand?
Yeah.
Okay. And we, from the question 1, we have known the W or the S equal the W over the double square root 3, right? Okay, combine this. And the R, we have known the R equal W, right? So the U times W equal the W over double 3, okay? And we can cancel the W, right? So the U is the limiting, right? The limiting 3/6. Here's the limiting, right? And right now, this is limiting. It's the limiting equilibrium, right? Okay, understand, right? So if you want the whole object is always equilibrium, okay, so the U must greater than and equal square 3/6. Okay, understand that now?
Okay.
Okay, and let's to take a review the steps that we have done. Okay, according to the topic, okay, so we can sketch the basal graph. Okay, here's the ladder, here's the vertical wall, and the ground. Okay, and we have known the ladder is in a condition that equilibrium, right? Okay, and first, according to question 1, we have got the vertical equilibrium. Okay, according to the vertical equilibrium, we got the R, okay, the R equal the weight W, right? And second, take moments about the base of the ladder, okay, about base of ladder, and we can got the clockwise moment equal the anti-clockwise moment, okay, and we know the S is normal reaction from smooth wall, the S the produce the clockwise moment, okay, and so the S times sine 60 degree, and for anti-clockwise moment, we know the weight that will produce the anti-clockwise moment. So we got W times 1 over 2 and times the cosine 60, right? The horizontal part. Okay. And we cancel the W. Finally, we cancel the L. So finally, we got the S equal the W over double square root 3, right? No problem. This is question 1, detail steps. Understand? Hello?
Yeah.
Okay. And look at the question 2. The question 2. The question 2 want us to show that the coefficient, okay, and according to the horizontal equilibrium, and we have the one, the friction equal the S. The S is the normal reaction from smooth wall. Okay, and we got the U times R equal to S. Okay, and we substitute the S equal to W over W square root 3, and we got the coefficient U times W equal to W over the double square root 3. And finally, we got the limiting equilibrium, the condition, right? The limiting equilibrium is the coefficient equal to square root 3 over 6. Okay, and finally, if we want the object, the ladder, keep the equilibrium, the coefficient must greater than and equal to square root 3 over 6. Understand now?
Yeah.
Okay, look at this, the question 10. Okay, the question have drawn a graph. Okay, we have a graph. A uniform, here the uniform road XY has the weight. The weight is the 20 Newton and the length is 90 centimeter. The road rests on the two parallel pegs. Okay, here's the two parallel pegs. And with x above y in the vertical plane, which is perpendicular to the axis x of the pegs as shown in the diagram. The road makes an angle of 30, right? Of the 30 degree to the horizontal, okay? This one, and touches the two pegs at P and Q, okay? Where we have known the segment 9, the XP is 20 centimeter, SQ is 70 centimeter. The first question want us to calculate the normal component of the force on the road at the P at the Q, right? Okay, okay. Think about it, how to solve it. And tell me how you think. And tell me how you think.
I think
How you think of. Mm-hmm.
I think we find uh the weight. We put the weight at the middle first,
Mm-hmm. And then,
and then we use the moments.
okay, use the moment, no problem. Use the moment to get the equation, right?
Yeah.
And use the combine the equation to solve the normal component of the force on the road. Okay, and so the first the first okay the first question 1, and we suppose, okay, suppose, and we net the normal, right, at P as the NP equal the normal, right? The normal at P. Okay, and the NQ, the normal, right? I changed the R, right? Maybe R is more appropriate. Okay, the R, the RP, and the RQ, right? And represent the normal, right? Respectively at P or Q, right? Q, normal. Okay, and the center mass is is what? Cylinder mass. Cylinder mass is the midpoint, right? The problem now. Okay, cylinder mass. Okay,
Yeah.
understand?
Yeah.
Cylinder mass is what? Is the how about the 25, right? Okay, centimeter. Okay, the midpoint. Okay, and we have no the P from the cylinder mass is the 25, right? And the Q
Yeah.
from the mass is the 15, right? Because the distance between P and Q is the 40, right? Okay, we got the cylinder mass. The P a different point to the cylinder mass. Okay, and we take a moment. Which point is the pivot? Take a moment. Take a moment about which point. Which point is appropriate? P, right? Okay, no problem. So P is the pivot. Okay. Okay. If I take the moment about P, so we can got the equation, right? The equation, we have to know the weight is 20. Okay. So the 20 times the what? And we want to is the pivot. Okay. Understand? The weight
Yeah.
is 20. Okay. And the so we want to get the horizontal part, right? From the cylinder. Okay. This horizontal. Okay. So the 20 times what? Times 25 and the cosine, right? 30, right? This is the horizontal part, right? Understand? Okay. No problem now. And equal what? There's normal. Okay. The normal AQ. The normal AQ. Okay. The normal AQ and what? The normal. We don't know the normal component, right? And I suppose the normal component is the NQ, right? And times what? Times what? Times what? Times what? It's 40, right? Because the pivot from the distance between the P and Q is the 40, right?
Yeah.
And but I want to got the horizontal, right?
Yeah.
Okay, so it's the 40 times the cosine is 30, right? It's times and cosine is 30. Okay, and the separating variable. Okay, and I found the NQ equal what? Equal 20 times the 25 times the cosine 30 and over the 40 times the cosine 30, right? And finally we can get the answer, right? Understand?
Understand.
Okay, so the NQ is 2. So we got this the 12.5 Newton. Okay. Okay. After that, we can use the vertical equilibrium. Equilibrium. Okay. To find the NP, right? The RP, right? The NP is the RQ, right? Understand? No problem
Okay.
now. Okay, and the vertical equilibrium in the vertical equilibrium, and we have known the NP, the NP plus the RP plus the RQ, right, equal to the weight, right? The vertical. Understand? Right? No problem now. Okay, the weight is 20, right? Understand?
Yeah.
And we have known the okay, there's we have known the RQ is a 12.5. Okay, so 12.5 plus the RT equal to 20. So the RP is 7.5 Newton. Understand right now?
Yeah.
Okay, the first and the way to analyze the graph and suppose the different point the normal action at P and Q is the R, right? And take the moment about P and the step the equation. Okay, the first we find the RQ, the normal reaction at Q, and use the vertical equilibrium, and we find the R at P, right? Okay, no problem now. Okay, look at question 2. The question 2 want us the coefficient of the friction between the rod and each pack is U, okay? And given that the rod is about to slip and to find the coefficient U, right? Okay, so the rod is about to slip, right? To find the U, the coefficient, right? So the rod is about to slip. No problem. Okay, understand? Okay, so first we have to analyze the force. Okay, the friction acts up on the stop at P, right? Understand?
Yeah.
Okay, first look at graph to find the friction. The friction acts acts up acts up the stop at P. Okay, and down the stop at Q, right? At Q. Okay, so we can go to the limiting friction, right? The limiting friction. So we can establish the equation. Okay, limiting equation. So I suppose the friction at P equal the coefficient and RP, right? And the friction at Q equal to the coefficient times the RQ, right? No problem now. Understand? Mm-hmm. Is there any problem in this equation?
No.
Okay, and after that we can resolve, right? Resolve the parallel to the road. We can resolve parallel to the road. Okay, so we can got FP according to the graph, FP, okay, plus the, or equal the FQ, right? And plus the 20. The 20 is the weight, right? and times what? The sine. Okay, sine 30, right? Because I make the component, right? Understand? Make a component of weight, right? This one, understand? The 20 sine 30. Okay, understand? The problem? Is there any problem?
No.
Okay, and after that, and take the value into equation. This one is the u times the 7.5, right? And FQ for FQ, right? FQ is 12.5 is the u times 12.5 and plus the 20 times the 0.5. Okay, and finally we can get the 7.5 u equal the 12.5 and plus the 10, right? And finally we can get the shift is what? Mm-hmm. And we got the 5. So finally we got the coefficient u is what? Mm-hmm. It's what? Mm-hmm.
Negative, I mean,
Non-negative. Mm, think about it. Oh, there's the friction. The FQ is negative, right? Okay, here's the negative. Okay, understand? Okay, because the friction is opposed to motion, right? So the friction the P and Q is the upward along the incline, right? Okay, so we got the 7.5 U plus the 12.5 U, right? And equal to 10, right? There's the 20 U, right? Is the 10, right? Finally, we got the U is what? The coefficient is what? Mm-hmm.
0.5.
Yeah, 0.5. Okay, finally we got answer. Understand now? Look at graph. Okay, understand now?
Yeah. Yeah.
Okay, look at question. Okay, let's take a review here. First, after the question 1, we have found the different normal reaction at P and Q. Okay, and the question 2. Okay, and we have first we have to distinguish the friction, the direction. Okay, the friction direction. Okay, the friction is the opposed motion, right? Okay, so we have no the friction direction is the incline upward along the incline, right? Okay, and the component of a weight is the downward along the ramp, right? Along the incline. Okay, and so we can establish the equation, right? This one. Okay, this one and this one. Okay, so FP plus FQ, right? Equal what? 20 times sine and 30, right? Understand? Now, okay. And combine the question one, we have calculated the value, take into the equation, right? And we got this one, okay? And finally, the coefficient we got, understand? Now,
Yeah.
okay, look at the question 11. Okay, look at the graph, look at the topic. Here's a ladder, the ladder X and Y. The ladder, the length is L, okay, and the width is W, and has its end X on the rough, okay, the end X on the rough horizontal ground. The coefficient of friction between the ladder and the ground is the 1/5, and the end Y of the ladder is resting against the smooth vertical wall. A window cleaner a window cleaner of the weight is long W stands at the top of the ladder to stop the ladder from slipping. The window cleaner's assistant applies the horizontal force. The force magnitude is P to the ladder and X towards the wall. The force acts in the direction which is perpendicular to the wall. Okay, and the ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes the angle theta with the horizontal ground, okay? And where the tangent theta is the square root 3, okay? So we can use the value to get the theta, right? Exactly theta. And the window cleaner is modeled as the particle, and the ladder is modeled as the uniform row, okay? The question one want us to find what? In terms of W, the reaction of a wall on the ladder, okay? Think about it. How to use the laws to solve the equation one. Mhm. We have the uniform ladder, the length W. Okay, the ladder length is W. Okay, and the length is L, the weight W, and there's the smooth. Okay, there's a smooth. Okay, there's a smooth, there's a smooth vertical wall. Okay, and the rough ground, right? Okay, and the rough ground. Okay, and we have the window cleaner weight, right, at the top, right, and just draw the graph, right, simply. Okay, and we have the cleaner weight non W at the top. Understand the pronoun?
Yeah.
Okay, and there's the tangent theta. Okay, and we have know the tangent theta is square root 3. Tangent theta square root 3. Okay, tangent theta square root 3 represents theta is the 60 degree. Okay, okay. The first question one. Okay, question one want us in terms W. In terms of W, the reaction of wall on the ladder and Y. Okay, the letter Y. Okay, so we can analyze the reaction from the wall at the top S, right? Okay, top S. So we use what? Which law that we might use? Mm-hmm. Moment, right? In this chapter, the moment law is always the we use. Okay, so we can take the moment about what? About this one. Okay, the base.
Yeah, the base.
Nice. Okay, take a moment. Take a moment about the base. Okay, now we have analyzed which force acting on the ladder. Okay, and the first that we have the weight is vertical. Okay, and the length. So the W and W times the L, right? Over 2, and the theta is the 60, right? So the length is the cosine, right? Horizontal part, right? No problem. Okay, this one. Understand? Understand the problem?
Yeah.
Okay. And now we have put plus the what? Because here's the cleaner, right? Okay, the cleaner's weight is the line W, right? No problem. Look at that. Because the window cleaner of the weight line W stands on the top, right? So here is the weight, is the line W, okay? And so we have to plus the line W times what? The perpendicular distance is what? Mm-hmm. Times what? Think about it. Times what?
Uh.
This one, right? The horizontal part, right?
Oh yeah,
Okay.
yeah, yeah, yeah.
And the so the L cosine 6 degree. Okay. Final equal what? Equal what?
D-
Equal
Uh.
what? Is the S, right? Supporting force, right? Is S times the L. The vertical is the L base sine 60, right? Understand?
Yeah.
Okay, so we can use the solve equation. So and the answer is the W over 4, okay, and plus the 9 W times 1 over 2, and here the right side the S times the square root 3 over 2, okay, and combine this one, so is the about the 9 the W plus here's the 9 is the 18W, right? And the right side is the S times square root 3. So finally, we can get the S is the 19W over the double 3. Understand? Now, the question 1. Okay, no problem. Think about it. Is that right? Is there any problem about the equation?
Oh no, no.
Okay, and the question 2. Question 2. The question 2 want us to find in terms of W the range of the possible value P for which the ladder remains in equilibrium. Okay, for the range of the possible value P. Okay, and so we have to use the resultant force. Okay, because the object keep the equilibrium, right? The range. So we use the range of P for equilibrium. And so we use the horizontal, right? Horizontal, horizontal, horizontal. Okay, horizontal. How to analyze this one? So at P, right? P plus what? Friction, right? Okay, equal. This is S, right?
Yeah.
Equal S, right? Understand?
Yeah,
No
yeah.
problem. Okay, and F is friction, right? And the vertical, and the vertical. Okay, and the vertical in the vertical equilibrium, so the R equal the W plus the line W, right? It's the 10W, okay? Understand? So here's the limiting. Here's the limiting friction. Friction is what? The force, right? The force is less than or equal the coefficient times R, right? Understand? Is the 10 mu W, right? Okay, understand? No problem now. No
Okay.
problem now. Okay, and we have to analyze the following one. Here's the two cases. The first case is the letter about. Letter about. If the letter about to slip outward or inward, right? If a letter about the outward slip, about to slip word. Okay, so we got the friction equal the UR, right? And the second, if the letter about to slip inward, right? If the
Yeah.
letter about to slip inward, okay, so we can got the friction equal to negative, right? R, right? Understand? And we can combine this one. Okay, take this equation, right? Understand? No problem.
Okay. No, no problem.
Okay, okay. And because the F equal S minus P. Okay, so take the equation. And this one is the value. We have known S is the 19W over square root S. So the answer is 19 square root 3 over 6W minus the term mu W. And right, okay, so we can take the range of the P and the 19 square root 3 over W, right, plus the 10 mu W. Okay, understand? No problem now. Uh-huh. Hello, understand?
Yeah. Okay. Okay.
Okay, so this is question 2. Okay, and as for the question C and D, look at them. Question C and D. Okay, just state how you have used the modeling assumption. Okay, here's the modeling assumption. Think about it. The assumption is what? The ladder is uniform. Ladder is uniform in your calculation. The assumption is so simple. What is assumption? Have you ever thought about the weight? The weight. Okay, think about this assumption related to the weight. Might be the uniform road, right? Because in this topic, we use the law related to the uniform road, right? Understand?
Yeah. Yeah.
So the assumption must be related to the uniform road. So okay, as for the uniform road, so the weight, okay, so the weight must, right, must x at the midpoint, right? Okay, at the midpoint of the ladder, right? No problem now. Understand? Okay, this is the assumption that we make. Understand now?
Okay. Yeah.
As for the final question, and just stay with the rhythm, the effect this that we have on. Okay, in practice, the ladder is wider. Okay, in practice, the ladder is wider and heavier at the bottom. The model is adjusted to the ladder is modeled as long uniform road with its center of mass closer to the base. Okay, just stay with the rhythm. Just stay with the rhythm. The effect this will have on. Okay, the effect this have on. This is the question one. The magnitude of the rhythm of the reaction of the wall on a ladder and why. Okay, think about it. The question one, how to respond. The magnitude of reaction of a wall on the ladder and why. Because if you have the wider and heavier right at the bottom, right? So
Yeah.
the clockwise, so the counter, or so the clockwise, they will produce the clockwise plus the moment. That's the moment they will produce the clockwise moment from which, okay, from which is smaller, right? Understand, right? So less anti-clockwise, right? So the less anti-clockwise plus moment, right? From S is needed. Understand? No problem now. Okay. This is question one. As for question two, the range of a possible value P for which ladder remains the equilibrium. Okay, think about it. If I want the range of the P becomes wider, okay? So if the range of the range of P becomes wider, right? Becomes wider, okay? So which means the equilibrium just easier, right? Understand the problem now?
Yeah.
Okay. So and how to respond? How to respond? So we can respond like this way. The no, the lower S means what? Means less, right? Less horizontal, right? Horizontal force require, understand, and which means the ladder, okay? Ladder, okay? The ladder is more stable. Understand? This one.
Okay.
Okay, the three questions in a little bit complicated, okay? And I will send the note for you, but you, after that, after the lesson, you use the notes to analyze the every single question, okay? The every single question, Okay, think about the
Okay.
process and the details and why I write in this way, why I use this law. Okay, understand? This is the math part. Okay, no
Okay.
problem.
Yeah.
Okay, and I will give you the new homework. Okay, remember to do it.
Okay. Okay.
Remember to do it. Okay. How about your next time is when? Is what that time? Next time.
Maybe Monday.
Okay, no problem. Okay, I will give the notes sent it to you. Remember to finish the homework, okay?
Okay.
Okay, because this examination is upcoming. Okay, today's the lesson is over, okay? And I will give your homework and then you need to finish it.
Okay. I will. Yeah.
Okay, bye-bye.
Okay. Bye bye. Who's watching me, eh? You guys been watching for 4 minutes? What the hell's wrong with you? Who's watching me right now? You know I wasn't paying attention to class, right? I was just so tired. Is it funny, baby? What is wrong with you guys? You guys are watching me. For what? Why would you watch me? Yeah, that's how tired I am. Looking sharp, my friend. Looking sharp. Okay, what I'm gonna do is we've been streaming for 3 hours. I'm gonna go take a nap and then go work out at 6 o'clock. So I'm gonna come back and continue studying after I'm done with napping, working out, and eating dinner. And then I'm gonna go through this tuition again. I'm gonna go through this again. Oh man. I'm gonna go through it one more time. Go through it one more time and then go through the second lesson one more time. Something went wrong. Don't worry, I already have it all recorded. Someone's AFKing on my stream. But anyhow, I will be taking a nap, working out, eating some dinner. And then I'll come back, finish physics, go through the homework as well. And then hopefully start on math, and then hopefully finish on math, and start on chemistry. Alright, that's all I gotta say.